Alright, hello everyone, welcome back. Today we're going to be starting a new series with dynamic systems and vibrations, and we are going to be starting off a little bit of math review. Today we're going to be going over separation of variables, first order ODE. So one thing we know for a fact is that this separation of variables can apply to variable coefficients, nonlinear, inhomogeneous ODEs that are first order. So let's look at an example. So for today's example, we have 5y dot plus 3y is equal to 0. And for this, we can describe y dot as dy dt. So let's know what we're given. So looking at this, this is a first order ODE. This is also a homogeneous ODE. So we can use separation of variables, and just to put icing on the cake, we know that this is a constant coefficient. It has constant coefficient. Let's plug in dy dt for y prime and divide by 5. So this is going to give us dy dt plus 3/5 y is equal to 0. This is going to put us in the position so we can actually use separation of variables. So next up we have dy dt is equal to negative 3/5 y. And now since we have the equations on each side, we can then move the dy divided by y onto the left and the dt over to the right. Next up, we can then integrate this function. So with this, now we can integrate both sides, and for the left, we are going to be shown that the integration of 1 over y dy is equal to the natural log of y plus a constant c is equal to negative 3/5 t. Of course, this is very nice, and then we have to add the c onto the right side as well. We're going to be labeling the constants as C1 and C2. But with the known laws with constants in ODE, we can describe the combination of both constants as a regular constant C3. So then that's going to give us the natural log of y is equal to negative 3/5 t plus C3. That was a kind of a terrible t, times t plus c of 3. So, and after this, we can then use our exponent function e. Just give me one quick second. There it is. Okay, so we can then use our exponent function e of ln of y is equal to e negative 3/5 t plus c3. So the e and the natural logs cancel out in this form. So we're then left with y is equal to e of negative 3/5 t plus our constant c of 3. And with this, we can actually split it up with, just to simplify the equation a little bit more. So we have e of c of 3 times e of negative 3/5 t. And we can simplify this once more with e to any constant, for in this case, is going to be y is equal to c times e negative 3/5 t. And that is going to be our answer for example 1. So then, moving on to example 2, we have a swimmer of mass lowercase m dives into a pool with initial velocity of 4 meters per second. Our water resistance can be described as b times v, which is a very simple form of drag. And our b in red is quote-unquote a damping constant that we can just label as a letter. So we can start off by drawing a free body diagram with a little diving platform and the beginning of the diver. So for the diver, we can model him as a single person while a force F is acting upon him, and the drag force of b times v is acting against the force he is putting into the water, which is his swimming power. So for this, we can then use the sum of all of our forces. So then that's going to give us F minus b of v is equal to mass times acceleration. For acceleration in this case, we can actually describe it as dv over dt, as acceleration is the derivative of velocity. So this equation by itself does not mean a whole lot. But what we can do is that we can then manipulate its variables so that we can get our true ODE that we can solve for. In its current form, it is not a standard form ODE. So, what do we have to do? The exact thing that we did in example 2. We are then going to have to move most of our variables around a little bit. So then that's going to give us, on the left side, m of dv dt plus bv, our drag force, is equal to f, our force. Now, what is most important about this is that the diver itself has not hit the water just yet. So we can then describe that during the dive, our force is equal to 0. So for this, we can then have m dv dt plus b times v is equal to 0. Now this grants us our standard form, as we are given a v dot and our v in this case. And because of this, it is now in standard form. We could use the exact same principles that we have reviewed in the previous example. So we can then find out that our velocity equation is equal to c times e to the power of negative b over m times t. And that is our answer for the velocity.